Brad Williams, Frugal Finance, the basic building blocks of a zero coupon bond. In valuing contracts promising a stream of known cash flows, the place to start is a listing of the market prices on pure discount bonds. Treasury bills, for example, also called pure discount bonds. These are bonds that promise a single payment of cash at some date in the future called maturity date. Pure discount bonds are the basic building block in valuing all contracts promising streams of known cash flows. This is because we can always decompose any contract, no matter how complicated its pattern of certain future cash flows, into its component cash flows. Value each one separately and then add them up. The face value or par value on a pure discount bond is its guaranteed cash payment. The interest earned by investors on pure discount bonds is the difference between the price paid for the bond and the face value received at maturity. Thus, for any pure discount bond with a face value of $1,000 maturing in 1 year and a purchase price of $950, interest earned is the $50 difference between $1,000 face and the $950 purchase price. Keep in mind, you always buy these at a discount. Zero coupons. Buy them at a discount. $50 is the interest earned, and the yield, interest rate, on a pure discount bond is the annualized rate of return to investors who buy it and hold it until its maturity. For a pure discount bond with a 1 year maturity, like the one in our example, we get yield on 1 year bond equals face value minus price divided by price. 1,000 minus 950 divided by 1,000 equals 5.26. So here's an example. If you pay $950 for a $1,000 bond maturing in 1 year, what is the yield? Not yield to maturity. Face value, 1,000. Purchase price, $950. Term 1 year. Here it is. Rates using Excel. 1. Look at that. We have number of periods. No payment here. So just leave that blank. Move on to present value. We know it's $950 and it's going to grow to future value of 1,000. The end result, 5.26. What if you paid $10.50 for the same bond? What is the yield? Not yield to maturity. 4.76. Why? Because you're paying $50 more than what you're going to get at maturity. 1,000 minus 150, 476. If, however, the bond has maturity different from 1 year, we would use the present value formula to find its annualized yields on this bond as the discount rate that makes its face value equal to its price. This is where people stumble because we have to determine the present value for each period. Here we have 3 years, 1, 2, 3. We have a price, 95, 88, 80. What's its yield? We're going to take the purchase price, just use 100, divide that by C43, by its price, minus 1. That's fine, that's simple. Second, this price, we can go through and we can do the simple math here to determine the 88. Let's just work this out. I did it this way. We can do it a couple different ways. We can take 100 divided by C44. We could do 1 divided by 2. We can do this. Edit, copy, edit, paste. We're going to go 1 D44. We're going to go C44. And we're going to go 1 divided by 2. We're going to get the same thing if we use square root 100 C44 minus 1. A lot of different ways to do the math and get the same result. If we have a price of 80, we're going to take the same format, 1,000 divided by its price, power 1 divided by 3 minus 1. Come up with this 772. So you're going, so what, Brad? What does that mean? Well, that's the yield. That's what you're going to earn for this period. There are 2 alternative ways that we can use to arrive at correct value for the security. In other words, we're going to add these 3 up and come up with the price. There are a couple different ways to do this. The first uses the price in the second column of 8.1, and the second uses the yields in the last column. Example 1 multiplies each of these 3 promised cash flows by its corresponding per dollar price and then adds them up. So 100 times 95, 100 times 88, 100 times 80 equals 263. The resulting estimate of the security's value is 263. What happens? 3 years, it goes from 263 to what? To 300. Example 2 produces the same results by discounting each year's promised cash flow. So what we did is we took 100 divided by 1.0526 to come up with this number. Here we took 100 divided by 1.0662 to the second, and then we took 100 divided by 107.72 to the third year, and we summed them up. Note, however, that it would be a mistake to discount all three cash flows using the same 3-year yield of 7.72 per year listed in the last row of table 8.1. If we did so, we get a value of $2.59, which is $4 too low. Is there a single discount rate that we can use to discount all three of the payments the way we did using present value 1 plus R to the n divided by I to get a value of 263 for this security? The answer is yes. The single digit rate is 6.88 per year. To verify this, substitute 6.88 for I in the formula for the present value of an annuity, as I did here. All I did is I referenced J61. This number you can change. I can change it to 7. And notice what the price did? It went to 262. If we go to 9, what happens? 253. If we go to 8, we get 257. You need to match this 263, 688, and this is just trial and error. Been doing it for a million years, and it works. The problem is that the 6.88 per year discount for the 4-year annuity is not one of the rates listed anywhere in table 8.1. We derive it from our knowledge using trial and error. We can summarize the main conclusion from this section as follows. When the yield curve is not flat, when observed yields are not the same for all maturities, the correct procedure for valuing a contract or a security promising a stream of known cash flows is to discount each of the payments at the rate corresponding to a pure discount bond of its maturity and then add the resulting individual payment values. That's critical. Why? Because we're going to delve into this in depth. And we're using zeros in order to build a term structure, price, specific types of securities. More to come, lots more to come. This is just a warm-up. Brad Williams, Frugal Finance. Thanks for watching.